Welcome to this fifth meeting of PRIMO Talk series. Today's speaker is Marco Viola from the University of Campania, Vanvitelli, and he is also one of the organizers of these seminars. Marco will talk about combining Newton type and steepest descent direction to achieve global convergence. Please.
Oh, thanks for the introduction, Serena. I cannot say thanks for the invitation because it's like I invited myself, but I can thank, for example, Pasquale to push me to do this talk and all you to coping with my will of doing this talk today. And so today I'm going to talk to you about a joint work I did with Daniela Di Serafino from the University of Naples, Federico II, and Gerardo Toraldo from the University of Campania, Luigi Vanvitelli. And as it's clear from the title, the main topic is globalization strategies for Newton type methods. And this is the outline of the talk. I will start talking about the Newton method, just give you a short introduction, which is not needed actually in this community, but I will do it as well. And then I will show you some ad hoc globalization strategies for Newton and quasi-Newton methods, and introduce you our method, which is called the steepest descent globalized line search method. And I will show you with some numerical experiments that it's an effective globalization strategy, but also something more, and you will see why. And then for sure, there will be some concluding remarks. So let's start with the Newton method. No need to tell too much about the Newton method. Suppose you are in the nice situation of minimizing a nice and smooth function, which has to be at least twice continuously differentiable. Suppose that we call its gradient G and its Hessian H. What does the Newton method do? Well, at each point, it builds the quadratic model of that function. It finds the stationary point of that quadratic model and takes it as the next iterate. And everything can be summarized in this way. So this is the so-called Newton direction, which is the result of the solution of this Newton system. Now, the Newton method, it's extremely powerful. Everybody knows, and it's one of the first methods people study. So in particular, you can prove this local convergence with superlinear rate. So if you are in the nice situation in which X star is a local minimizer in which the Hessian is strictly positive definite, it's Lipschitz continuous in a neighborhood of X, you are lucky enough to be in that neighborhood and you use the Newton method, then you will converge quadratically, which is nice. But it seems that there are maybe too many conditions in order for this to happen. So let's try to break them a little bit and see what happens to the Newton method, just for fun, let's say. So let's start with a nice convex function in one dimension. This is the primitive of the one of the primitive of the arctangent function. So its gradient G is the arctangent. The Hessian H is this nice function, which is always positive. So convex, perfect. Well, what happens if you start the Newton method from, let's say, 1.39, you will suffer a little bit at the beginning, but then in 5 iterations, you will converge to the exact solution. And this is the nice behavior of the quadratic convergence of the Newton method. But you just need to move slightly to the right, and everything is broken. You start from 1.4, the method diverges. And function is nice, it's convex. So here you can see that important property of being close enough, and in particular what is called the basin of attraction of the point X star. Well, so let's move on. Of course, this is an extreme case, and maybe you can think that with a line search you can fix things. So just to introduce something which doesn't need to introduction in this community, again, what is a line search strategy and how does a line search globalization strategy work? Well, the direction of movement of the Newton method is good. It's just that you move too much, maybe. So if you take a line search, you will converge. So a line search method in general works like this. You have a direction D, which is, you should be at descent direction. And then at each step, you try to find the step length alpha k, which guarantees you some condition. So in order for a method like this to be globally convergent, you need mainly two conditions, which are sufficient to have convergence. So the first one is on the direction. The direction has to satisfy at each step this condition, which regards the cosine between the direction and the antigradient, which has to be strictly bounded from 0, which means that the angle should be strictly bounded from the 90-degree angle, which gives you no descent at all. So once you have that all your direction are nicely descent direction, let's say, you can perform a line search, and for example, a simple Armijo backtracking can help you obtaining global convergence. So our idea will be try to stay in this framework of line search method, so in order to globalize Newton type methods. So just to make you understand what does this condition on the angle means and what can happen to that angle, to that cosine, let's take another nice and convex example. In this case, it's in 2 dimensions. This function is e to the power of x minus x plus 2 e to the power of y minus y. This is the gradient, this is the Hessian, and you can see the Hessian is a nice diagonal, strictly positive, definite matrix. And but if you think about it, according to the value of x and y, it can be quite ill-conditioned, because e to the power of y or can explode, for example, if y is positive, or become very small if y is negative. And also for e to the power of x. And in general, what you can, if you do some easy computation, you can take the relation on the cosine and prove that actually this cosine between the Newton direction and the antigradient is bounded from below by the condition, which means that if you have a good conditioning, then you are sure that the angle will be good. If you are a bad conditioning, and for example, that this lower bound is close 10 to the power of minus 5, for example, you have no guarantee at all that the direction will be good enough, and you may have some troubles. And in order to make this more visual, if you plot this function between minus 5 and 5 and minus 5 and 5, so you see it's nice and convex, you can see from the contour plot. But if you are in the region in which x and y have different signs, you will have one element of that diagonal which becomes very large, the other one which is small, and so the problem can be ill-conditioned. And you can see that from this plot, as soon as you arrive in this bad region, the condition number goes up to 10 to the power of 3, and that cosine goes down to 6 to the power of minus 2. And visually, they are quasi-orthogonal directions, so there's no way the Newton direction can be a nice and the best direction to take in this case. And this is the same if you go on. So also here in this fourth sector, you will have the same behavior. Now, we have now more or less understood what can happen. So which bad things can happen in the case of a convex function. But what if I'm in the non-convex case? Well, the non-convex case, things can get also worse, because you have the quadratic model around a point could be a concave model, and the stationary point then could be a maximizer. Hence, your direction could be an ascent direction. There is no way you can satisfy a line search. Just to give you also in this case a visual example, if you take this nice, let's say, function, which is an 8th-degree polynomial introduced by Goldstein and Price in the 71, and this has 4 local minimizer, which are these 4 points. Particularly, we will focus on this one, which is minus 0.6, minus 0.4. in which the function value is 30. This is the function. I plotted that for you, and observe please that here on the zeta axis I have the log 10 of the function value, because it will explode at the boundaries of this, and otherwise you would have seen a really flat region at the center, despite this is not even close to be a plateau. So the 4 local minimizers are really distinct. So what happened? Suppose you start close enough to this point I indicated to you. If we can visualize it in 2D with the contour plot, you start here, Newton direction goes towards this direction, you perform line search and stop here. Second step of Newton with line search and you stop here, and then suddenly you compute the Newton direction, the steepest descent direction. The Newton direction is an ascent direction, and the method stacks in 2 iterations. And there is no way you can perform whichever number of line searches you want, but you will never be able to descend starting from an ascent direction. So what can we do, and what has been done in literature in order to overcome all these troubles you can have with Newton method and Newton type methods? So in case of the Newton method, the idea is based on the same, on the thing I showed you about the line search method. So you need that your matrix is sufficiently positive definite in order to have convergence, to ensure your convergence. Because if the matrix is sufficiently positive definite, you will be sure that the angles between the Newton direction and the gradient direction will be small, or at least as small as possible. And so what can be done? The idea is that you can start from the matrix, the Hessian matrix H, and add something in order to make it positive definite. Well, this something could be, for example, a multiple of the identity, which allows you to shift the spectrum towards the right and ensure that all the eigenvalues are positive. But you can see that this is quite a complicated strategy, because at each step you should devise a different lambda, and to do so you maybe should try a lot of values for lambda, or maybe compute some eigenvalues that can cost a lot. Luckily enough, there is a smarter strategy to do this, and it's via modified Cholesky factorization. So the idea is that you start to compute the Cholesky factorization of the matrix H, the Hessian, and then as soon as the Cholesky method discovers that there is a non-positive diagonal element, it will add some quantity to ensure that it becomes sufficiently positive. And you can actually discover that if you do this in the Cholesky factorization method, what you will end with is the Cholesky factor of some modification of your original Hessian, which is exactly what we are looking for. So you have the Cholesky factor of a matrix H tilde, which is HK plus EK, where EK is a non-negative diagonal matrix. And then, of course, once you have the Cholesky factor of this matrix, solving the system is straightforward and you can move on. So this is the case of the Newton method. What happens, for example, if you go to quasi-Newton methods where you do not have the matrix? For example, in the BFGS method, there are a couple of interesting strategies devised in the early 2000s. So just to understand what happens with the BFGS method, everybody knows it. At each step, you approximate the Newton system with the second system, where BK is an approximation of the Hessian, and it's computed iteratively like this, where Y and S are respectively the difference of the gradients and the difference of the iterates. Now, if you start from a nice symmetric positive definite matrix B0, you know that at each step K, your matrix will remain strictly positive definite, given that the scalar product between Y and S is greater than 0. And as you can imagine, when the function is non-convex, this can be negative. And if you update the matrix, you end up losing the symmetric positive definiteness, and you can never recover it. Now, what you can do? The two strategies I told you before, devised by Lee and Fukushima, are based one. So the first one is the modified BFGS, in which the yk vector is replaced by this y bar vector, which is nothing more than yk plus some term, which is a multiple of the vector s, chosen such that the scalar product between y bar and s it's sufficiently positive definite, so ensuring that everything will go well during the iterations. Another strategy is the so-called BFGS with cautious update, CBFGS, in which given to constant key and upsilon, what you do is just that you check at every step if the scalar product satisfies this condition, which means that it is sufficiently positive definite. And if and only if this is satisfied, then you perform the update on the matrix. Otherwise, you stay with the previous approximation. And between these two, the second one, it's far more efficient from the computational point of view. So now we are seeing what has been done in literature. So it's time to introduce our idea. And our idea is try to introduce something which is more flexible and which can be adapted to various Newton type methods. So what is the steepest and globalized line search method? Idea. Suppose that you're in some point in which the Newton type direction, which can be Newton, quasi-Newton, inexact Newton, or whatever you like, does not satisfy the angle condition you need for convergence of the line search method. So what you can do? You can think of considering a convex combination between the Newton direction and the steepest descent direction, so the gradient direction. And so you can take a direction dk dependent on a certain scalar beta, which is the coefficient of this convex combination. And if you take this beta equal to 0, you will get the gradient direction, equal to 1, you will get the Newton direction. As you will notice here, we didn't consider just the gradient direction, but a scaled version of the gradient direction. This has a twofold meaning. The first one for sure is that, okay, Newton direction is good as it is, so usually in the Newton method, you take the full step on Newton direction, and maybe you start with line searches. But with the gradient, you cannot do that. You will need some step length. But so this is a way of having two reasonable directions if you have beta equal to 0 or equal to 1. But it's also another, there is also another advantage in having such a kind of direction. Because consider the case in which your function is scaled by a value omega greater than 0. Well, you know that if the function is scaled, the gradient is scaled as well. But the Newton direction is scale invariant because you will have the Hessian is scaled and the Hessian -1 is scaled with 1 over omega. So the Newton direction is invariant, but the gradient direction may start to shrink or expand. So if you have a suitable choice of CK, for example, you can take Barzilai-Borwein step length, which are such that they scale with 1 over omega. Then you will recover scale invariance of the direction. This is a nice feature of this methodology. So we take this direction. So what do we do? At each step, so supposing we have a starting point x0, a sequence of values for our threshold on the angle condition. So we compute the matrix xk, which can be whatever you want. We compute the Newton type direction, and then we check. Is the angle criterion satisfied? If so, then we take the Newton type direction. Otherwise, we compute the step length CK, so being sure that it's a good step length. And then we try to find the beta k such that we can have a direction dk which satisfies the angle condition. Once we have found this direction dk, then we can perform the line search and everything is fine. So now the question which arises is, can we actually determine beta k? And the answer is for sure yes, otherwise I wouldn't be speaking today. So let's start with a theoretical result. And it's regarding the existence of an optimal beta k. And I will explain you why optimal. So suppose you are in the case in which the Newton type direction does not satisfy the angle condition. So this cosine is smaller than epsilon k. you can build a nice second degree polynomial in beta, which is this nice polynomial here. This polynomial is such that the two roots of this polynomial give you the direction for which that cosine is exactly epsilon k or minus epsilon k. So if you take the smallest one in 0, 1, which is the closest to the gradient, you will be sure that if you build up the direction in this way, we can call this optimal beta, beta epsilon k, you will have that the direction satisfies the angle criterion, the angle condition as an equality. So just to give you an example, imagine you are again in that bad situation on the Goldstein price polynomial in which you get stuck. So if you suppose that you take as scaling factor for the gradient this ratio between the two norms, it's just an example to have the two direction well scaled, let's say. So what you can do is you build up the polynomial is as this form. It has the roots, two roots in 0, 1 in this case, because it was a quite an obtuse angle. And the first root is this one, so around 0.5. And if you plot the cosine between the possible direction dk beta and the minus gradient, you see that before that threshold, so before that beta epsilon k, everything is fine. The cosine is greater than your epsilon k, which is in this case is 0.5, and you can take actually every direction in this range and be sure that the method will converge. So it's also in this sense it's optimal, in the sense that it's the largest you can take, let's say, so the closest to the Newton method, or the Newton type direction. But our idea was to try to see if we actually need this, in the sense that suppose that your epsilon k is very small, you're going to take a direction which has angle exactly epsilon k, so it could be a bad direction as well. So maybe we can try to find a lower bound for this beta, taking some smaller value, which is reasonable enough. So if you start from the condition on the cosine, you do some computation, which I won't do now, but you end up finding that a sufficient condition for this to hold is that your beta is smaller than this beta hat, where rho k and pk are defined here. These are two nice positive quantities, so you're sure that this is a value between 0 and 1. And this has a nice feature, because this form allows us to understand better what is going on. Because if we rewrite pk, we can see that it's a multiple of the difference between the cosine and the threshold we have fixed for the cosine. And so if this value of the cosine is close to epsilon, then the Newton type direction is good, and beta hat tends to 1. So we can take a Newton type direction. Otherwise, if it's very small or close to -1, this goes to 0, and we are forced to take the steepest descent direction. So everything is very automatic. Just to give you an idea of the difference between the optimal and the suboptimal choice, this is an example with the Gulf research and development function from the Morey-Garbo-Hillstrom problems. And we plotted for each iteration the optimal value, which is the red circle, and the suboptimal value, which is the blue cross. You can see it's usually smaller equal. It's always smaller equal. And here you can see the cosine you get from the direction. So here in the black cross is the cosine between the Newton type direction in this case and the gradient direction, which can be very bad. Here the sequence of epsilon k is a decaying sequence starting from 0.5. You can see that usually you get smaller angles, so larger cosine if you take the suboptimal step. And this somehow could favor nice properties of the gradient descent, and we will see this later. So before moving to the results, just a couple of theoretical results to prove that everything is nice and everything can work. Of course, we can prove global convergence. It's not outstanding because we tried to follow step by step what we needed to have the global convergence of a line search method. So if you have the epsilon k, which is bounded away from 0, then since we are using our Armillo backtracking, we can prove our results only in terms of limit point of the sequence xk, which will be all stationary. And then, since this is a globalization strategy, you would expect that if you use it, for example, with the Newton method, you can recover the nice properties, local convergent properties of the Newton method. So, and actually you can do this. So we have a local quadratic rate for convergence in the case of the Newton method, which simply says that if you take the Newton direction, and the epsilon k is a nice non-increasing sequence bounded away from 0, supposing that there is this limit point of the sequence, which is nice, and where the hypothesis of the Newton, the local convergence of the Newton method are satisfied, so the positive definiteness of the Hessian and the Lipschitz continuity, then if your lower bound on the epsilon k it's chosen to be small enough, you can recover actually the Newton method that you have the quadratic rate of convergence at the end. So they say, let's try to see if this works. And so some numerical experiment. Just a quick note, we developed a MATLAB implementation of this method. As suggested previously, we are using one of the Barzilai-Borwein step length. In particular, we are choosing the BB2 step length, which has been chosen in some preliminary test against the BB1 and some alternating strategies. We take a decreasing sequence epsilon k starting from a fixed value epsilon 0, which we make vary a little bit. And so we actually decrease epsilon every time we reject the Newton direction. The notation we use, I will indicate with this with this code, let's say SDG NT epsilon 0, where NT can be either Newton or BFGS, indicating the kind of second order method we are globalizing, and epsilon 0 is the value of this starting point of the sequence. We use Armillo backtracking with quadratic interpolation. The stopping criteria is on the relative decay of the gradient norm. So first set of examples, some non-convex problems from the J. Barker collection, which include Moregard-Bol-Istrom instances. We have 36 problems, 10 starting points for each problem. So we take the original one and 9 random around it. In total, 360 instances to use to compare the methods. And we will compare the Newton version and BFGS version of our method, respectively, with the modified Newton with Cholesky factorization from Fang O'Leary, and the CBFGS, so the BFGS with cautious update of Lie Fukushima I introduced you before. First of all, let's see what happens to the choice of bit. As you may recall, we had this optimal version, this suboptimal version, and which may differ a bit. And how they perform? Well, we performed a comparison. In black, you will find the suboptimal choice we proposed. And in blue, you can find the optimal one, so the one guaranteeing that the cosine is exactly epsilon k. And as you can see, the suboptimal one outperforms the optimal one in terms of efficiency and robustness in terms of time, number of iteration, and is slightly less efficient, but more robust in terms of number of function evaluation. And this is in the Newton case with epsilon 0 equal to 0.5. And also you can do the same comparison on BFGS, and here the difference is it's more evident, and you can see that the suboptimal choice is very good. And as I said, this is likely due to the fact that at least in the first iterates, you are giving a bit more freedom to the gradient method. And you know that the gradient will be, the gradient descent, it's a nice method to arrive to a good region in which to then push with something else. And so now we have seen that the suboptimal choice proposed is the most effective one. Let's see what we can do against state of the art. This is the Newton case. So against the modified Newton with Cholesky factorization, we are more efficient and more robust in terms of function evaluation, slightly less efficient, but equivalently robust in terms of number of iterations. Just saying that we had to perform a comparison on iterations and function evaluation because the implementation we had of the modified Newton was quite slow. It used some max files which were not optimized, and it would have been very unfair to compare it because the time of our method on MATLAB resulted to be 2 orders of magnitude smaller. So it would be very, very unfair. And if we move to BFGS case, we can see that in terms of iteration, we are slightly more efficient than BFGS and CBFGS. And actually, you can see that the CBFGS appears to be worse than BFGS, which can be expected. So if you have an instance on which BFGS functions really well, it's efficient, it's difficult that modifying it, you will obtain something better, but still, we are slightly more efficient here in terms of objective function evaluation, slightly less robust, but more or less we are competitive. But as I said, this is not only a globalization strategy, and we'll tell you why. Let's put ourselves in the convex case and consider the problem of training a linear classifier with the regularized logistic regression model. Everybody uses this kind of model nowadays. They are quite common in machine learning. And so let's see what happens. We have chosen 14 classification data sets. We adopted a 10-fold cross-validation setting. So we have a total of 140 instances on which to compare our algorithms. This is just a short description of the dataset. I can skip it. So results. First of all, let's repeat the comparison in terms of iteration and objective function evaluation to see optimal versus suboptimal. And also in this case, as it happened for the BFGS case in the non-convex instances, you can see that in terms of iteration and objective function evaluation, the suboptimal choice is more efficient and more robust. If we now try to compare our method with BFGS and CBFGS, first of all, we can see that CBFGS is useless. We are in a nice convex case, so there is no need to globalize BFGS. It can work really well. But we are able to outperform it both in iteration and evaluation. And this is due to the fact that we are nicely combining BFGS with the gradient. And now the question which may arise, we started from 0.5, which means that more or less a 60-degree angle, it's enough. What if at the beginning we push a little bit more towards the gradient? And we tried this to test this. So we consider the BFGS method with 2 different values of epsilon 0. Previously we had 0.5, now we tested with 0.9. So at the beginning, we are quite strict on the direction to take. We want to use something which is really close to the gradient. And you can see the performances improve a lot in terms of efficiency and in robustness. And maybe you can think that this could suggest that then if I take just the gradient method, it will be better. But this is not the case. If you compare with the BB2 gradient method, which is the one we use inside our algorithm, you see we are far more efficient than the gradient method because we are using properly the BFGS one, and we are more or less equally robust. Of course, this comparison may look unfair because, yes, we are comparing in terms of iteration and function evaluation 2 algorithms which are clearly different, because one is a first-order algorithm, the other one is a second-order algorithm. So each iteration, it's more costly. So maybe this one would think that this only can work in this kind of setting, and in terms of time, we cannot outperform. But actually, we performed a test also on this, and what you can see from this performance profile in terms of execution time, we compared the algorithm with 0.9 as a starting point, both with the gradient method with Barzi-Leiber-Wayne two-step length, both with the BFGS method. And the nice thing is that you can see it's clear from this picture that also in terms of time, you can outperform both of them in efficiency and in robustness, at least for robustness with respect to BFGS method. And this is a clear image, which at least for me and for Daniele and Gerardo tells that we are doing the very smart thing in combining these two directions in the right way. So we are taking the best of the two methods, the gradient method and BFGS method, and combining it, obtaining something which can perform far better. And this is it. So conclusions. We proposed the steepest descent globalized line search method, which is a globalization strategy for Newton type methods, which combines Newton type and steepest descent direction. It's far more flexible than standard strategies. Imagine that you have a case in which you cannot compute the Newton direction and you have to use inexact Newton. What does it mean to perform the Cholesky modified factorization if you cannot even solve the Newton system? So here instead, you just compute something, you check the angle and you move on. So it's far flexible, and we showed with extensive computational experiments that we can outperform or in general be very competitive with state-of-the-art globalization strategy devised ad hoc for Newton and BFGS method, but also that this is not just globalization strategy, it can also be considered as a smart way of combining the first order method and second order methods. So in the future, we would like to analyze the application of this kind of strategy in more interesting setting with respect to the unconstrained, really smooth setting we are in. So our hope is to devise a way of applying this to constraint optimization or also on stochastic optimization, and hopefully in the realm of non-convex optimization in the training of neural networks, for example, in which you see lately a lot of interest has been put for the use of BFGS in order to outperform the naive constant step length gradient method which are used in literature. So maybe you can, if you can find something which can take the best of both, it could be better, and we hope to find something interesting in the sense in the future. And that's it. Thanks all of you for your attention. If you have any questions, feel free to ask. If you are too shy to ask or you don't have the time, you can take some time and look at our paper, which has been published a few months ago on applied mathematics and computation. And if you want to try the code, we have on GitHub the MATLAB implementation, which for the moment includes Newton, BFGS, and LBFGS methods. And that's it. Thanks a lot.
Thank you, Marco. Actually, we're perfectly on time, so we have time for questions.
For once in a lifetime.
And so you can unmute yourself or use the chat, so please.
May I ask a question? So, okay, thank you. Thanks for a very nice presentation, Marco. As I said, it was a pleasure also joining this meeting all together. I have a curiosity. What about the scaling factor you have in front of your gradient? So CK, okay, the parameter CK, you have an update for that parameter. So
that is the Barzi-Leiber-Wayne step length. So at the beginning, I start with, let me just go to the...
My question was about how relevant is this choice for this parameter? Because if you have a poor choice for this parameter, what happens to the performance of your method?
Well, okay. We perform, first of all, let's say, combining Newton and gradient direction is not, you know, a game-changing idea. It's something which has been suggested by Bertsekas in its book 30 years ago, more, also previously. And there is a paper from 1996 which we found and from which we extended the theorem I showed you on the beta k. In that paper, for example, they used 1 as scaling factor for the gradient. And so they said, okay, Newton and naive gradient direction, let's use them. And we made some tests. For sure, 1 is not a nice choice with respect to scaling of your function. If you try to just change the scaling of the function, you can see that you can suffer a lot from that and giving more or less importance to the gradient method. So from that point of view, 1 is very bad. Everything which scales with 1 over omega, let's say, as if you see the example before, it's fine. We made some, so lately the Bards-Leiber way in step length have been used extensively in many fields because they are proving to be very effective. So our idea was, let's try to use also them in this way. So our comparison was only on Bards-Leiber-Wien-like strategies, and I didn't show anything regarding that comparison, but we performed comparison with Bards-Leiber-Wien 2, Bards-Leiber-Wien 1, and ABB mean. And we chose BB2 because it proved to be more effective in terms of time, iterations, objective function evaluation. And an idea on that is that, well, for sure, ABB mean is not great in this sense because we are ruining a little bit the sequence of iterates of ABB mean. We do not perform at each step the computation of CK, so there's no chance of obtaining something good in that sense. But actually also the BB1 step leg didn't work as well as the BB2, and maybe because it was too large. So we have conjectured that maybe the BB2, it's short and it's reasonable enough to give you something. And it can allow you to push your second order method towards a better direction, and you are happy with that, more or less. But I have to say, we haven't then explored further on this choice on CK to try some other strategies. Could be interesting, but I think we are happy enough with the Bards-Leiber-Wien 2 for the moment.
Okay, thank you so much.
You're welcome.
Any other question?
May I ask one, Marco? It's
yes, of course.
The discussion you make on the possibility of the line search to fail because of the angle of the fact that in Newton direction may be a poor descent direction,
yes,
is frequently overcome by the trust region approach. The dogleg is a
yes.
path which goes from the gradient, the steepest descent direction to Newton step. Have you made a comparison with that approach? Because in some sense, your step is on a dogleg.
Yes, this is something we thought about because actually, if you take the dogleg method, you can see that it's a combination of the gradient and the Newton direction. But it is based on a different, let's say, trust region method are based on a different second order model in which we analyzed a little bit this in the paper, but I have to say we didn't compare with trust region strategies. And so we didn't explore this, and maybe we can do in the future in order to see how this compares. We focused on the fact that we were using line searches, and so we stick with the use of line searches as a globalization. So, but I think that this is something we will do in the next future to see, because yes, the combination, if you rewrite trust region methods and dogleg methods in the right way, you will find something like this, with the only difference that here we have a convex combination, there you don't have that. You have just a linear combination of the two. but I have to confess we didn't make tests in that direction.
Thank you.
Other question?
Sorry, can you hear me?
Yes.
I have a curiosity about the more or less one of the last slide where you compare with the gradient method.
Oh, repeat, please.
In one of the last slides, there is a comparison with the gradient method.
Here.
The other one?
This?
That one, yeah, sure.
Yes.
This is in terms of execution time.
Yes.
And you perform better than, this is the Barzilai-Borwein method.
This is the gradient with Barzilai-Borwein two-step.
Barzilai-Borwein method. So, and here you use 0.9 in the.
Yes. Yes. So at the beginning, I give more freedom to the gradient, let's say, in that sense.
So at the beginning, you are more closer to the
gradient direction. Yes.
Yeah. But at the end, it's less expensive, even if you have a second order method inside, because it's strange.
Yeah. So consider that at each step, we always compute the BFGS direction.
Yeah.
So the cost in terms of the cost per iteration is exactly the same of the BFGS method.
But you are faster.
But we are faster because we take, and as you can see from the plots in terms of iteration and function evaluation, we take far less iterations. This is comparison with 0.5. This is 0.9 with respect to 0.5. So we take, although the iteration have the same cost, we take far less iteration. That's why we outperform BFGS in terms of time as well. And
so it seems that
yes.
So it seems that in these problems, the BFGS direction is not a good direction.
It's not that it's not good. I wouldn't say it's not good. I would say that it's not ideal at the beginning.
Yeah, okay.
Because still, if you just use the gradient direction, you don't do better. And CBFGS here, which more or less tries to compensate with possible bad behavior of the BFGS matrix, behaves exactly like the BFGS method. So they are not so bad. Of course, in this kind of setting, we have a logistic regression. You can have some cases in which if you are in the wrong point, the Hessian matrix is very ill-conditioned because you have the exponential. But more or less, this was fine. So these were nice tests for BFGS. And on this kind of instances, for example, also LBFGS is flawless. And so I wouldn't say it's a case in which BFGS is bad. It's just that maybe at the beginning, especially, the gradient helps you going better towards the solution. Mm-hmm. So in the good area. And then you can give freedom to BFGS for the convergence. And we have seen actually that our choice of beta more or less reflect this. So at the beginning, it's more gradient. And once the epsilon case is small, our choice favors usually the full BFGS step when we are. And so I think the difference is mainly due to the beginnings, the initial steps.
Thank you.
You're welcome.
Any other question? Actually, I have just a curiosity. You mentioned the ABB mean. Yes. So you say that you try. I want just to know how you can manage alternation strategies in this this case.
Well, we have made a test. I have to say that maybe there could be smarter ways in doing that. The idea is that I computed the ABB mean step length as you will do in general with a standard gradient method with variable step length. So I have memory tree and the usual threshold. I had also the adaptive strategies on the balance.
Ah, okay.
So it was the smart way, but it wasn't sufficiently good in this kind of problems. And I think that because since if you take the ABB mean step length alone, it is very good, but maybe then you take a completely another direction. So all the nice properties on what happens to the eigenvalues of the error. So you don't have any. You cannot keep the iterates of the ABB mean step length. So that's why maybe it was not so nice in the performance. I have to say, but the comparison it's really close. So the choice of BB2 proved to be the best in our preliminary test, but it's not that ABB mean was awful. It was good as well, but slightly worse than BB2.
Mm-hmm. Okay, thank you.
You're welcome.
No other question?
I think I have a question in the chat, but no, it's a
yeah,
private
let
message.
me.
No.
Ah, okay. Do you want to reply publicly?
Yes. The question was, did you check this approach combination of direction deep learning with non-convex objective function? And the answer has been given during the talk. So it's our aim for the future, because the idea is that one. So that's the direction where we would like to move.
Okay. If there are no other questions, I would like to thank you again for your interesting talk.
Thanks.
And just to